Chapter 3, Section 2. We are going to continue with a lot of the same ideas from that first section. Here it says, an exponential population model. This is the same thing as we just went through a problem. Population at time t equals its initial value times some base raised to the t power. Well, the base right here, if the base is greater than 1, we know it's exponential growth. And so if I'm adding some growth rate, exactly 1 multiplied by 1 is 100% or staying the same thing. You multiply by 1, nothing changes. So anything bigger than 1, I am increasing. And whatever I have bigger than 1 in my base is the growth rate, the rate at which I am growing. That's as simple as that thing is right there. So they say as long as that rate is greater than 0, 1 plus r is going to be the growth factor. 1 plus r is the growth factor. R is the growth rate. Where did it say it? Somewhere they're going to have to say it. Percent rate each year. There you go. Right there is that rate each year. Now if my r is less than 0, so 1 plus like negative 0.2, well then it would be smaller than 1. And so I would have an exponential decay function, and I have a decay factor that is going on. Whatever that base, it's the growth factor or the decay factor. So it says finding growth and decay rates. Tell whether the population model is an exponential growth function or an exponential decay function, and find the constant percentage rate of either growth or decay. That's the R is what we are looking for. So let's look at this. This is our original value. There is our base. Is that growth or decay?
Growth.
Growth. And the R is 0.0136. That's what's bigger than the 1. Or if I wrote it as a percent, I could say 1.36%. That's the growth rate. Whatever that is, San Jose is growing at a 1.36% growth rate. So here we have Detroit. There's the original. Here is our base. Growth or decay?
Decay.
Decay. How am I going to find the R of this one?
1 minus this number.
1 minus this number. What do you get? 1 minus 0.9858.
0.0142. Right.
Does Jackie know what he's talking about? So when they say it's rate of decay, 1.42%. Whoops, 42%. Look in the book. Did they do a negative, or are they just wanting us to call it decay and call it a 1.42% decay?
Decay of 1.42.
Yeah, that's usually what we say. It is negative. It is negative. We're going down at that rate.
You just use the 0.985 rating as the positive, right?
If we just use, say that again? As long as my base is less than 1, it's going to be decay. I'm going to be reducing at this rate, 1.42% in this case. And if it's bigger than 1, I'm increasing at this. So it would be possible to say, oh, the R is a negative. The R is a negative 0.0142. Nothing wrong with that. Or we could say we're decaying or declining at a rate of 1.42%. So like I say, just compare the book and see how they wrote it the same way. Because either is okay. Finding an exponential function. Determine the exponential function. It happens to have an initial value of 12. It's increasing at a rate of 8% per year. No problem. I'm going to say y equals. We could say f of x or whatever. 12. There's my initial. Multiplied by 1 plus 0.08. 8% is 0.08, and we're increasing, so we're adding it to the x. There it is. There's the equation. Suppose a culture of 100 bacteria is put into a petri dish, and the culture doubles every hour. Predict when the number of bacteria will be 350,000. This is my initial bacteria. This is what it's being multiplied by every hour, or that is the base. Remember when we first did the exponentials, the thing I keep multiplying by each time? That's the base. Well, if I'm doubling, I'm multiplying by 2 every hour. So the population at time t, we'll write it this way. Initially, I had 100 times 2 to the x. I'm doubling every hour. And x then is going to be 2 to the t, since I did p of t. And this is going to be time in hours. It needs to be the unit that they are working with up here. Predict when the number of bacteria will be 350,000. I just figure out where does it equal 350,000. So I can do my y equals 350,000 on the calculator, and we can see where that intersection is. Bingo, there's the intersection. It happened to be 11.77 hours later. So just like what we've been doing before, really nothing new. The only thing new is recognizing how I can write the equation from the values they gave us. We're going to do that again down here using something from science. Radioactive decay, do you remember what that is? Or maybe you haven't studied that in any class. I think you probably have.
Radioactive decay.
Radioactive decay, it's going to be exponential decay. You can see again on the graph there, I've got a black exponential decay going on. Radioactive elements, back there on our periodic chart, anything past number 83, so starting at polonium, 84, is radioactive. It will naturally decay, and in physics, we'll study that in more detail later on, but it will naturally decay into lesser elements. And so radioactive decay is an unstable parent atom nucleus that will decay into daughter nuclei that are earlier on the periodic chart. And we often talk about how quickly it decays by the term half-life, which means how much time it will take until half of the original has decayed into a different element. Suppose the half-life of a certain radioactive substance happens to be 20 days. There are 5 grams present initially. Well, let's just start right there and write ourselves an equation. I'm going to say the population at time t, since I kind of like that. Population at time t equals, well, what's our first number?
5.
5, that's our initial. And then what is happening? Half-life is half of it has disappeared.
1.
I'm multiplying by 1/2. That's my base. Half-life, 1/2. Now it takes 20 days. The previous one, it just took 1 hour. If I back up to this one, I could call this t over 1, time every 1 hour. But this one is going to be t over 20, because it takes 20 days for this. So 1/20th, this happens every 1/20th. So you get 20 1/20ths, and you have half of it gone by then. So it happens every 20 days, we just go t over 1/20. And find the time when there will be 1 gram of the substance remaining. So we just want to know when does this thing equal 1. So once again, we can graph the first one, we can graph the second one, and somewhere it will intersect, and it happens to be after 46.4 days. It's in days. After 46.4 days. It'll be in the same unit that they have it in. This is an easy section today. Scientists have established that atmospheric pressure at sea level, 14.7 pounds per square inch, and the pressure is reduced by half for each 3.6 miles we go above sea level. Find the altitude above sea level at which the pressure happens to be 4 pounds per square inch. We're going to go to our calculators on this one. But first I need to write an equation. Population at some altitude, so I'm going to call it P of A, equals, can you help me out? 14.7. I initially, at sea level, that's my initial value, 14.7. Times 1/2. It's reduced by half, so I'm multiplying by 1/2. Times 1/2.
T over A over 3.6.
Since I am using A as my variable, I'll say A over 3.6. And this happens to be the altitude in miles. So my answer is going to be in miles. They want to know, when do I get to 4 pounds? Well, let's try it out. I'll even use the calculator instead of the Desmos on this one. See if I can move my calculator so it comes in the screen. There we go. So y equals 14.7 times 0.5 raised to the, and I'll need parentheses, x. If I divide, what is it, 3.6? So there's 1, and then I want to know where it reaches 4, right? So let's make my second one at 4. I'm going to zoom fit. Let's see what happens. Standard, probably not quite high enough in the Y, which I, of course, could adjust. Maybe it would be, I don't know. Well, that zoom fit isn't doing any good, is it? Let's go to zoom standard, 6. There comes our pressure. There we go. It did go high enough. So we just want to find the intersection, right? Calculate intersection, first curve, second curve, my guess. I'm probably close enough. It'll find it. There we go. 6.76. What?
It should be
6.76 miles. We're finding altitude is what the answer is. Yes. Altitude is going to occur at 6.76 miles up. Modeling U.S. population using exponential regression. Jackie loves these. Use the, now notice carefully, 1900 through 2000 data. I even emphasize it down here, not the 2003 data. The 1900 through 2000 data in Table 3.9. An exponential regression to predict the U.S. population for 2003. Compare the result with the actual one. So here's one, we did this with Dallas last time on our own, but here's one they are doing. Now I want to show you, we've done it on our calculators, but I want to show you how you can use Desmos and do all this stuff. So I'm going to need, I wonder if I can click and drag that. No, I can't. So I'm going to need to, there we go, everything's in my window. I'll show you what you can do in this, because often you may be where a computer is and it's such a big, pretty screen. I want to add a table to it. So my x sub 1, y sub 1 values, and I can even change a color if I want to right up here. Just hold that down and we want to go to, we're going to have red dots. All right. So my x sub 1 values, I'm going to use 0 for 1900. And what is it doing? Every 10 years?
10 years.
All right. And then my y's, 76.2. Somebody might, whoa. 76.2. What's the next one?
92.2. 106. 122.2.
122.2?
123.2. Wait, oh, no, it was 123.
This one?
Yeah.
123.2.
132.2.
Say that again.
132.2.
Thank you.
151.3. 179.3. 200.3. No. 223.3. Come on. 226.5. 248.7. 281.4. That's it.
Is that it? Now, what we do on this, again, let me get it into my record window. I should have recorded the whole screen. What we do on this is,
Same as doing it in our calculator, right? Just add.
it's different on this. I need to go down here to a new one. On your calculator, you'll do stats and you'll do exponential regression, because that's what they said, right? What I'm going to do here is I'm going to say y1, and that'll do y sub 1. Then I'm going to hit the tilde, it's called, approximately equal. And then I'm going to write an exponential equation. What does an exponential equation look like? A times B raised to the x, right? And I'm going to say x1 for x sub 1. So what it has done is it's going to take what I have told it, and it will tell me the values that make it fit. There's my A value. There's my B value right over here. So I'm going to capture that a minute. So I have my equation, and it also tells me some other things, but I'll capture that. Notice over here, it has also put it into, now my window's not very well, my screen, let's not worry about it. But it's graphed it all there. So here I have my values on it. And they say then, okay, figure it out for 2003. Well, I have a population at time t, 82.719 times 1.0125 raised to the t. So what would I do to get the answer for what's the population in 2003?
Substitute 100.
I'd substitute 103 in. Did you guys do, I don't know if you did it on your calculator or you were just watching me do it. Well, let me come over here, and I did it on the calculator earlier, and I substituted 103 in. And I got an answer of 304 or 305 million. Now, how does that compare to what it actually is? Not real close. We're 14 million off, aren't we?
It sounds like this city cannot hold that population.
Remember, when we're talking about population growth, there's a better model than the exponential ones. What is that better model? We have a limit to growth. What are those called? Logistics models. Logistics growth, the logistics model. Now, what does a logistics model look like? I'm going to change this thing up here. Instead of y sub 1 equals, remember what logistics growth? They were C, whoops, wrong thing. C divided by, there it is. 1 plus,
some number.
oh, look it back up. Did they do A, E? And I'm going to use the one with the E in it. I think they said AE. I don't see it written right now. A times E raised to the negative K, and I need to do X1. There we go. So it says, all right, I can figure logistics model. It's this one right here. Now I'm going to go ahead and put that function in so I can substitute on this. And I can just say y equals, I can give it a function if I wanted to. So what's my C? 798.8? 798.8 divided by 1 plus, what's my A? 9.1897? 0.1897 times E raised to the negative 0.016038. I'm going to say X. Whoops, yes, that's right. X. I'm going to turn this one off. Probably didn't even see it disappear. Now I am going to change my grid just a little bit. X-axis, maybe negative 10. And we were going to 103, so maybe I'll go to 120, anything that's bigger than that. Y-axis, maybe negative 1,000. Whoops, 10,000. And our population, oh, just a minute, it was 300 and something?
Yes.
I'm going to go negative 10 to 400. That'll just get it where it works a little better. So you notice, and by the way, the R squared, this gives me the R squared. I should have pulled out that other one. It's really pretty good there. But now, oh, I can't do y of x. I need to do it as a function. G of x. Oops, f of x. That works. I want g of x. Now I'm just going to substitute it by telling me g of 103. Now what is the answer?
Really close.
Yeah. My answer now is telling me that when I substitute 103 in, I am getting 289.2. And what is it? 290.8. Much better model. So their question was, compare the results. Well, if I was writing the comparison, that 304.7 million, that's kind of high. Not real good. A logistics model, when we did it gave us much better results for it. Maximum sustainable population, there's our logistics model. That top value over there. Says, okay, use this table from 310. Now get your calculators out. We're just going to work in our calculators, and we're going to play around with this, how we can do more than one at the same time. Use the data in table 3.10 and logistic regression to predict the maximum sustainable population for Florida and for Pennsylvania. They want us to graph those models and interpret their significance. So on your calculator, let's go to our stats, and in list 1, let's do 0 through 100 for our years. List 2 make Florida, and list 3 make Pennsylvania. So we're doing it all in our lists. 0 through 100 and going by tens. Once I have my data, I want to do my stat plot, second stat plot. Plot 1, scatter plot, and it's list 1 versus list 2. Now I want to do zoom stat, but before I do that, I forgot to clear out my equation. I'm going to hit y equals and clear out my equations that are back there. Then I'm going to go back to my stat plot and enter on my 1. So I'm ready to graph this one, and I want to zoom stat. I think it's choice 9. Zoom stat. There we go. This is Florida. I'm going to go back to my stat plot, and I'm going to go to plot 2, turn it on, and this time, now I choose scatter plot, this time I want list, can you tell me what I'm trying to graph now?
3.
It's 1 versus 3.
What you had to
So to get list 1, it's right above 1. I have to hit second and then 1. There's my list 1. 1 versus 3. And I also want to choose a different symbol. I use that little square, so I'm going to use the little plus. And I can show you on yours if you have a slightly different model. And now when I hit graph of this one, there goes Pennsylvania's. Now it's logistics growth as well. It's just started higher, and it's evening out sooner. It has a limit to its growth a little sooner. Logistics regression. I'm supposed to do regression to this. So we remember if I go to second, I'm sorry, not second. If I hit stat and go over to calculate, Now we're going to do a little bit extra this time. I'm going to find Logistic. There it is, Logistic. And I'm going to hit enter, but then I'm not going to hit enter again. I am going to tell it what data in the table I want the regression done on, and I'm going to tell it to store the formula for me. So here we go. After I hit Logistic, I'm going to say list 1. So second 1 will give me list 1. List 1, comma, which is right above the 7, comma, list 2, second 2. I'm telling it it's list 1 versus list 2, comma. Then I'm going to go to the variables, and I'll be doing this a second time, so you can watch me again. I'm going to hit this variables button. And I'm going to arrow over to Y variables. I'm going to choose function, and I want to put this regression equation in the Y sub 1 list. So I'm just going to hit enter. And there I have told it to do logistics regression, list 1 versus list 2, and store it in the Y sub 1 location. Now when I hit enter, it will think a little while. Logistics are the most involved. And it will think a little while. And it will think a little more. And then it comes. Now, I don't have to write this down. It's in the form C over parentheses 1 plus AE to the negative, and they said BX instead of KX. If I hit my Y equals button, guess what is automatically entered in Y sub 1 for me? The whole thing. Now I'm going to quit out of this, and I'm going to do logistics regression on Pennsylvania. So we'll go through the same steps. My stat, over to calculate. I'm going to choose logistics. There it is. And then I am again going to tell it, second 1, list 1, comma, list 3, comma, my variables button, arrow to Y variables, select function variables, and this time I want to put it in the Y sub 2 location. And then when I hit enter, it'll think about it. And it will calculate the logistics regression. There we go, a little faster on this time. If I hit the Y equals button, I not only have the Y sub 1, but there I have the Y sub 2 already entered for me. Now, if I just capture this screen for just a moment. Oh, wrong one. Let's get rid of that. Leave this page. There we go. I capture that screen and paste it in here. Remember, this was Florida. This was Pennsylvania. And the C value or the top value, what does that C value or the top value stand for? The limit to growth. Now if I go back to my calculator and hit graph, it has those entered in, so there we go. There goes my 2 lines, fitting my 2 sets of data. And it says in our question, logistics regression to predict the maximum sustainable populations for Florida and Pennsylvania. And then we're going to interpret their significance. Okay, well tell me about Florida. What is the predicted maximum sustainable population?
To
28.02 million. Isn't this in million? What's my predicted maximum sustainable population for, what is it, Pennsylvania? $12.58 million. Now let's think about this for a minute. This is real world data. It's another thing I love about this book. It takes real world data. U.S. Census Bureau. It's where they got this data from, up through 2000. And there's been 2010, one more census since then, so we could figure out what that one is and add some to it. But this tells me something. This tells me that at the trend that has been going on, how big Florida is going to get to 28 million people. Why is Florida going to go to 28 million and Pennsylvania is only going to be 12 and a half?
Maybe Florida is more, here is bigger or something like that.
Maybe the land area is bigger. Good idea.
They have high level of the medical or something.
Why would Florida be more popular? Sometimes they're called snowbirds, those retired people that in the winter, they travel to Florida, and they don't like the winters in Pennsylvania, and so they move south, and this is the trend that's going on. People are wanting to move where it's a nicer place to live. They like the beach, they like the weather, whatever it happens to be. So this gives us a prediction. So if I'm going to interpret it, we would be writing a paragraph out about why we think Florida is where it is and why we think Pennsylvania is where it is. So this is really useful. See, I just get goosebumps of excitement for this stuff because I can know, hey, I know where Florida's probably going to end up, 28 million. Modeling a rumor.
Wow.
Watauga High School. Wow is exactly right. I think back here, you guys were pretty familiar with, this is no big deal, we're guessing populations. That makes sense. We can kind of guess where a population is going to go. But guess what? Anything I can collect data on and model mathematically, I can predict what's going to happen. Let's take a rumor. Watauga High School happens to have 1,200 students. Bob, Carol, Ted, and Alice start a rumor. This is not what you should do, but we're studying it in math. Which spreads logistically so that, and here's the equation, and I'm going to write it out again. These are the number of students who have had it T days after they started spreading this. 1 plus 3, 9 times e to the negative 0.9 t. So here's the formula that they have. It models the number of students who have heard the rumor by the end of t days, where t equals 0 is the day the rumor began, initial value. How many students have heard the rumor by the end of day 0? How would I get that answer?
X equals 0.
Yeah, my variable is 0. In this case, I'd put a 0 right over there. That'd be e to the 0, which is 1. 39 times 1 is 39. What's 1 plus 39? 40, so I get 1,200 divided by 40. 30 students. By the end of the first day, 30 students. How long does it take for 1,000 students to hear this rumor? Well, I can answer that. When 1,000 of the 1,200 students do it, you know how to do it. I'm just going to pull it over here. We would graph it out, and we would see where the intersection with our line, y equals 1,000, is going to be. And we might have to change our windows. And we discovered, 6 days.
It's only 6 days.
By the end of 6 days.
Almost the whole school knows that.
Almost the whole school knows it. 1,000 of the 1,200 students. Now, remember this thing peaks out. It approaches the upper limit of what?
Just only one.
Of 1,200 is what it approaches the upper limit of. But how long does it take to get there? You know, there's always 1 or 2 students that just never hear the rumor. I mean, that's the idea out there. Some of us are raising our hand. I never heard that one. Don't know how everybody else knows about it, but I never heard that one. Eddie, you said something a minute ago. You said, well, let's call it a disease instead. You're exactly right. Diseases are modeled. Remember when the big Ebola scare was going on over in West Africa, over in West Africa? How were they predicting how many people it might go to? Mathematical models is what they were doing to try to figure out what is that growth going to be. Can you see the goosebumps that are on my arms? You should be able to see those things. This is exciting stuff. Math is awesome.
Math is everywhere.
It is everywhere. It is incredible what it can do for us, the power of mathematics. I'm done. You can start working on your stuff.